So in testing the significance of the slope, for step one, stating the null alternate hypothesis, very important. And in this case, we're looking at a null of beta equaling 0 and the alternate hypothesis of beta not equaling 0. And let me just say here from the very beginning that if you're looking at this or if you're studying this in the book, then you're going to notice that they've actually put something different. On page 449, they have the null hypothesis as the beta less than or equal to 0, and they have the alternate as beta greater than 0. So this is, if you're looking in the book on page 449 and you're trying to understand this question, just know that it doesn't correspond directly to the slides. Yes, step one, beta equaling 0 and beta not equaling 0 is found on page 448 because that is the initial setup. But if you read further in the book, you'll see that the first step to set the null and alternate hypothesis is setting the beta less than or equal to 0 or beta greater than 0 as your alternate hypothesis. It could be either or, but I'm just saying in this case, this is what is being used. And this is relevant because when you're trying to look for that critical T in Excel, then, you know, using an alpha or an alpha divided by 2 matters a lot. Okay, so that's why I'm telling you this from the start. When we don't divide anything by 2, it's because we're looking at this particular setup here. Okay, the beta less than equal to 0 or the beta greater than 0. Okay, any questions on that? So step 2, select the level of significance, our alpha, okay, 0.05. Step 3, test a hypothesis about the slope of a regression equation using the t-stat. So again, we're coming back to the t-stat. Thus far, we've dealt with z's, we've dealt with t's, we dealt with f's, and we're back to the t's. It's because of the type of question that we're dealing with. For this analysis, there will be n-2 degrees of freedom, which we had earlier in this chapter. Formulate a decision rule. Formulate a decision rule. So reject HO if your T, okay, your computed T is greater than T alpha sub divided by 2, n-2, okay? So because I'm actually dealing with a beta that looks like this, or a hypothesis test that looks like this for my alternate, and then as I said before, I'm looking at this as my null, I'm actually not going to, well, let me say it like this. In Excel, I am not going to divide by 2, all right? I'm just going to take my alpha as is and take it by 0.05, okay? So if you go into Excel, I'm not going to show it because we've done it many times. If you go into Excel, okay, and you plug this in, you will get that answer, okay? You will get of course, negative 1.771, okay? And again, I'm saying 0.05 because our null and alternate are actually less than and greater than signs. They are not equal and not equal, okay? So and we've dealt with this type of thinking before. So that's where we get the 1.771. Make sure you go into Excel and do that. And what do we call this again, this 1.771?
The critical.
The critical what?
The critical value.
Right. We call it the critical T. Okay? The critical T. So that critical position or that critical number, as always, establishes our rejection region. Okay? We can't ever get away from that, and we can't really say it too much. Because if we are trying to establish a rejection region, okay, we have to first have our critical values. And if my alternate hypothesis is that, then I know I'm on the right side, and I know that my critical value, right, is that. And so the question at that point just becomes, does my computed value fall in the rejection region or does it not? Okay. Now, and I'll drop this into Excel in a moment, but if we take the sample, calculate the ANOVA, right, what do we see here? Well, we've already seen this, right? We know what that number is, the 0.26. That is our beta. Very important number, of course, tells us something about the relationship between a change in y over the change in x. Okay, as x goes up 1, y goes up 0.26. That's what we know. And then we also see this 19.98, meaning that if there are no calls made at all, still there will be 19.98 copiers sold during the period. Okay, so it tells us something about setting x to 0. We still have some value for the copiers, our y-intercept. We learned that last week. When you look at this new piece right here, this 6.205, we are calling that the t-stat. And we are saying that that t-stat needs to be compared to our critical t-stat. Okay, that is our computed t, or our test statistic, that's 6.205. Now the math for it is quite simple. If you were to do this by hand is what I'm saying, because we just need the beta. There are statistical reasons why there's a -0 there, but generally we can kind of get rid of that for where we are. And then the standard error, okay, 0.042. So if you take your beta over your standard error, you're going to get your computed t of 6.205. Okay, you don't have to do that math, because when you run your regression summary output, it's going to give it to you automatically. Interpretation. For the regression equation that predicts the number of copier sales based on the number of sales calls. Look at this. Look at this language. Copier sales based on the number of sales calls. So I'm selling something after I make some phone calls. The data indicate that the slope 0.26 is not equal to 0. Okay? Now I know that's obvious because 0.26 is a number, which is not 0. But really, that's what we're testing. Okay? So this number here of 0.26 represents the beta. And our hypothesis is that beta is less than or equal to 0. And then alternatively, beta is greater than 0. So looking at those two hypotheses, our null and our alternate, which of the hypothesis is consistent with the number we actually have?
The alternate would be the one that's greater than 0.
Right, right. The alternate hypothesis, okay? This number here represents what is, or not, can't say really represents, it's probably too strong a word, reflects what we actually have received in our summary output, because 0.26 is greater than 0. Now, we have not proven it yet. All we did was say, well, based on what I have, 0.26, I'm hoping that I can reject the null hypothesis. I'm hoping that when I finish doing this test, that this can be rejected. Okay, because if the null hypothesis can be rejected, then my 0.26 is what we call statistically significant, meaning we can make statements about it because we confirm its accuracy. We can use it as truth, okay, in making our business decisions. Okay, so just from the door, I need you to know that when you set up your alternate hypothesis, you're already rooting for, like in quote, air quotes, you're rooting for one of these to be rejected and one of these to not be rejected, because then you're done, okay? If it turns out that our null is not rejected, then you're not done, because you got something inconsistent with what your scientific test has kicked back to you. And so then you got to go look at your data. Maybe there's a problem in the data. But that is not this particular case. This has worked out. Okay. Therefore, this is where I am right here. The slope can be interpreted and used to relate the dependent variable, number of copier sales, to the independent variable, number of sales calls. In fact, the value of the slope indicates that for an increase of one sales call, and this is nothing terribly exciting, right? Change in Y over change in X. Okay? When we look at this is what we kind of have to see. So as there's an increase in one sales call, so there's an increase in one sales call, right? Because our X variable is the sales call. The number of copiers sold will increase by 0.26. So that's a plus 0.26. Okay, so that's our slope interpretation. If a salesperson increases their number of sales calls by 10, right, the value of the slope indicates that the number of copiers sold is predicted to increase by 2.6. And all that means is I'm increasing the sales calls by 10. So instead of 1, right, I have 1 times 10. So I go to 10, right, moving the decimal place over 1, basically. And then we move the decimal place over 1 with 0.26. That's going to give us a 2.6. Okay, so instead of, and let me erase this here, instead of 2.6, or instead of 0.26, we're going to get 2.6 because we effectively multiplied both of our numbers, our numerator and denominator, by 10. Okay, if it were 5, 5 calls, then we just multiplied both numbers by 5. That's the beauty of having a denominator of 1. The value of the slope indicates that the number of copiers sold is predicted to increase by 2.6. So the beta, and this is the fascinating thing, like the regression equation gives us so much information because the beta becomes a predictive tool, meaning as I increase X by 1, Y goes up by whatever the beta is. And then ultimately, the regression equation also gives us if I have, 20 calls, 20X, how many do I anticipate selling as the Y? So it's almost 2 built-in predictive tools in terms of that Y equals A plus BX equation. Okay, as in correlation analysis, please note that this analysis does not provide any evidence of a causal relationship, right? Meaning, as I told you last week, correlation, which is what we're doing, is different than causality. Another type of study is needed to test that hypothesis. Okay. Before we get to standard error, any question on that? Oh, and by the way, before I ask that, the reason why we rejected the null, let me get into that for a moment, because it didn't really say it that clearly in the slide. So as we go back to this, we established this as the rejection region, correct? And so if this is the rejection region, any computed t, and remember this is a line of t, okay, any computed t that falls in the rejection region will establish the fact that we reject the null hypothesis. Our actual number is 6.205. Okay, so clearly that falls way over here. Let's call it over here, 6.205, which means that we are going to reject the null hypothesis. So that's why we rejected it. Okay, keep that in mind. It didn't say it in the slides very clearly, but we established our critical region, 1.771, right? And that, of course, came from this math, or the t.inv, or looking in your t table. And then after we found that 1.771, right, we were then able to say, okay, if our computed t falls in that rejection region, we reject the null hypothesis. What is the null hypothesis? Again, the null hypothesis is that beta is less than or equal to 1. If we reject this, right, that means we are not rejecting this. And that means we like this. And if we like this, that means this 0.26 is what we call statistically significant.